Alright, well, this is lesson 5.3 in our book. Title of it is Solving Quadratic Equations by Finding the Square Root. Okay, a little pre-knowledge here. I want to go over some information that we probably should have picked up in the past, but just to remind you, some properties of radicals. And there's a product rule that says that if you're going to multiply two radicals, first of all, they have to have the same index. And let me tell you about the index. The index is this number in the V here. And of course, I don't see a number. A lot of times in mathematics, we have understood numbers. Because radicals are talking about repeated multiplication, the understood number in here is 2. Now, in other places, we have understood numbers as 1. Like if you have something like x, if you just had a variable x, then there's an understood 1 as its coefficient, and there's an understood 1 as its, I dotted in here, as its exponent. Okay, but with radicals, the number 1 in here wouldn't make any sense because it's talking about repeated multiplication, something that you can times by itself and equal a, whatever that number is. If I ask you a question, what is 3 times equal? You'd be saying 3 times what? Because you know that you have to have two numbers in order to have multiplication, period. So the only first number that makes any sense would be a 2, and for that we just don't write the first one. For some reason we have understood numbers, and that's understood 2. Okay, so to multiply two radicals, this is the radical sign. The number under the radical is called the radicand, and they have to have the same index, and these do. And so to multiply two radicals that have the same index, you get the same index, and you just simply multiply the radicands. It's called the product rule. And here we have the quotient rule. If you divide two radicals that have the same index, they must have the same index in order for you to be able to do it, then you simply divide the radicands, and it has this radical with the same index. Okay? Other things that need to talk about first here are what perfect squares are. Perfect squares are obtained when you raise something to the second power. For instance, if you take 2 and you raise it to the second power, that will be 4. 4 is a perfect square. 3 raised to the second power, well, that's 9. 9 is a perfect square. Interesting things about these perfect squares, and I'll go ahead and label this perfect square up here. I'll have to get, that's going to be an F. Let me get a little thinner line here. Hang on. Perfect squares, okay. They're the key, perfect squares, these numbers are the key to simplifying square root radicals, or where the index is 2. And of course, if you take the square root of 4, or the principal square root of 4 as we'll call this, then that's number is 2. And if you take the square root of 9, the principal square root of 9 is 3. These are numbers that you know the square root of. Square root of 5, well, 5 is not a perfect square, and if you plug that in the calculator, you'll find it's a repeating decimal. It goes on forever. So this is, you can't simplify these, but these you can. So what we want to know these perfect squares, because we're going to be dealing with square roots, and these are the keys to simplifying them. Okay, so down here, to simplify a radical with an index of 2, and that's the understood one, the one that's not written in, or the square root, you factor out the largest perfect square from the radicand and then reduce. Okay, let's move on to the next screen. Okay, so example number 1, I've worked it out already. We want to simplify, and I sort of implied the directions here, simplify the square root of 24. Well, as I think about the number 24, it is not a perfect square itself. That'd be the first question I'd ask myself. 25 is, but 24 is not. So the second thing I'm asking myself is, what's the largest perfect square factor of 24? And it's going to be 4. So I use that product rule. I say the square root of 24 is equal to the product of the square root of 4 times the square root of 6. And the square root of 4, I know that's 2. Thus, I've simplified it, and the square root of 24 is equal to 2 square root of 6. Go ahead and try this one. Okay, well, what I did while you guys were working on this is I wrote out the perfect squares down through 289, or 17 squared. And so you would want to be looking at 500 to decide if it is itself is a perfect square, and of course it's not. Then you want to find the largest perfect square that will go into it, and of course that's going to be 100 will go into 500. So we want to pick this one right here. So we're going to break this down into the square root of 100 times the square root of 5. And the square root of 100 we know is 10, and the answer is 10 square root of 5. So you can make this list on your paper pretty easy. Just take the integers and start timesing them by themselves and then writing it down. That'll help you on simplifying these. Okay? All right, let's take a look at the next problem. Next problem here, we have a multiplication problem with two radicals. Okay, first thing you want to do is to look at these and see if either one of these themselves can be simplified before we multiply them together. In 30, I don't see any perfect square factors, and I don't see any in 10 either. So I'm going to multiply these together, and I get 30 times 10, or the square root of 300. And then if I go back to my list, I know that the largest perfect square factor of 300 is 100. Its square root of 300 is the square root of 100 times 3, and I know the square root of 100 is 10, so I have 3 square root of 10. Now I'll tell you, when I look at this problem right here, there's a kind of little secret to figuring out what's going to go into it ahead of time. In other words, I know that 30 is 3 times 10, and when I multiply these together, I'm going to have two factors of 10, and that's the 100 that was a factor of 300, the perfect square factor of 100. So if I can find a repeated factor or a common factor between these two, then timesing it by itself is going to be probably at least one perfect square factor of the resulting radicand when we multiply. Go ahead and try this one. Okay, well, the first thing we'll do is look for perfect square factors in either one of these, and I don't see anything. But in my mind, I'm thinking 14 is 2 times 7, and 21 is 3 times 7. So I have two factors of 7 that are going to equal 49. So whatever this is equal to, I know 49 will go into it. It may not be the biggest one, but it'll get me started. So as we multiply these together, we get the square root of 294. Now, I don't know my 49 times tables, but I know that 49 is going to go into it because I had 7 in there twice. So I'm going to just divide in my calculator, 294 divided by 49, and it's going to show me that it's times 6, and of course the square root of 49 is 7. Simplified, we get the simplified answer is 7 square root of 6. All right. Another example. Now here we have two radicals with what we'll call coefficients on the radicals. These are numbers that are multiplied. You've seen them coefficients on variables before. With this problem, what we're going to do is just simply rearrange the multiplication. We've got really just all multiplication from one side to the other. So I'm going to take those coefficients and move them out front, and then I'm going to take these radicals and move them to the back and multiply the numbers times the numbers and the radical times the radical. And this should be a 2, not a 3. Let's change that to a 2. Okay, so 2 times 3 is 6. And in here, I'm seeing a factor of 6 in here, and here is a 6. So when I multiply these together, I get the square root of 72. But something tells me that 36 is a factor of it because I had two factors of 6. So that'll make a perfect square, and it's 36 times 2. So we have 6 times the square root of 36, which is another 6, times the square root of 2, and we wind up with 36 square root of 2 with this problem. Okay, you try one. Okay, well, we don't really have to rewrite this. In our mind, we can say 4 times 3, the numbers multiply to be 12, and then multiply the radicals together by multiplying the radicands, and we get the square root of 15 times 5 is 75. I got a factor of 5 in here, and I have a 5 here. 5 times 5 is 25, so I know 25 will go into this. So sort of obvious when you think about quarters. You know, the 3/4 makes 75 cents. And then we have 12 times the square root of 25 times the square root of 3. We have 12 times 5 times the square root of 3. And we have 60 square root of 3 is our answer. All right. Okay, now we're going to use the quotient rule. There's a couple rules about radicals and fractions that we have to observe as we simplify. And the first rule is that you cannot have a simplified expression with a fraction under the radical sign. And of course, that's why we're starting out with this problem. We got a fraction under the radical sign. The second rule is that you can't have a radical in any denominator of a fraction. Okay, well, we'll deal with that second one in a minute. First thing you want to do with this is to see if 7 over 16 would reduce. If it will, then that's what we want to do. We want to go ahead and reduce it, but it won't. And so the next thing is we use that quotient rule, which says the numerator and the denominator both get this radical. So it's the square root of 7 over the square root of 16. Now, we have a radical in the denominator. Pardon me there. We have a radical in the denominator, and we can't have that, but this one is a perfect square, so we go ahead and evaluate the square root of 16. We get 4. So this now is an acceptable form. There's no fraction under the radical sign, and there's no radical in the denominator. You try one. Okay. 6 over 25 doesn't reduce. We use the quotient rule and put both of the numerator and denominator under a square root sign. Square root of 6 does not simplify. Square root of 25 is 5. There's our answer. All right. Next example. Example number 5. 7 over 2 doesn't simplify. We put the square root of 7 over the square root of 2. Unfortunately, 2 is not a perfect square. We started out with a fraction under the radical. We got rid of that, but now we've got a radical in the denominator, which is the second rule about fractions and radicals. You can't leave it like this. It's not considered simplified. So what we do here is it's pretty simple. What we do to rationalize this denominator is we multiply by this radical factor of the denominator. Well, it's the only part of the denominator, but if there was a number 3 in front of it, I'd still be doing the same thing. My problem is the square root of 2. The way I get rid of that is I multiply by a 1 fraction, and that 1 fraction is going to be the square root of 2 over the square root of 2. Again, that's equal to 1, so I'm allowed to multiply by 1 anytime and not change the value. But I'm going to take that radical that's in the denominator, put it here and here, and this will rationalize my denominator. In the numerator, I use the rule for multiplying radicals. It's the square root of 14, or 7 times 2. In the denominator, it's the square root of 4, okay? And of course, the square root of 4 is a perfect square factor. Now we can simplify that as the square root of 4 is equal to 2, okay? Now, it is okay to say the square root of a number times itself equals that number. You wouldn't necessarily have to multiply it first. We know the square root of 2 times the square root of 2 has to equal 2. You could go straight to that step right there. All right, you try one. Okay, 2 over 11 doesn't simplify, so we write it as the square root of 2 over the square root of 11. Can't have a radical in the denominator. Rationalize the denominator by multiplying by the square root of 11 over the square root of 11. In the numerator, we multiply the radicands, we get the square root of 22. In the denominator, the square root of 11 times the square root of 11 is 11. Now, that's our final answer. There is a tendency to think that we can cancel the 11 and the 22, but this is really not 22. This is the square root of 22. It's 4 point something, and 11 doesn't go into this number evenly. So we got a rule about reducing, and that is that you can't cancel a number outside of a radical with a number inside a radical sign. It just doesn't work. Okay, there's our answer, and let's move on. Okay, now I want to talk to you about using the square root, or solving equations with the square root. Okay. Let me just read this to you. When we have the squared term, or x to the second, in an equation, and not the linear term, or the x to the first, we call it the linear term, we solve it like a linear equation, and we get the squared term by itself, and then use the square root as an algebraic operation to both sides. Okay, so I guess what we're going to be doing is we're going to be having an equation like x squared is equal to 4, and we're going to take the square root of both sides to get rid of the square. Now here's a fact. Square root and square are inverse operations. They undo each other, so when you have square root and square right behind each other, they cancel and you just get the radicand. Now this answer here would be x is equal to. Now the rule is that when you use it as an operation, then you have to look at both positive and negative roots. So when we take the square root of both sides, we have to preface our answer with a plus or minus. Okay? And that's what we're saying right here. We have to put that plus or minus sign in. Okay, first example here. I've already got it worked out, but I'd like for my class to go ahead and write this down on their paper, is to solve 2x squared plus 1 equals 17. Now, can you see that in y equals ax squared plus bx plus c, that the linear term is not here in this one? We don't have it. If that's the case, then the idea or the strategy to solve this equation is going to be to isolate the squared term and take the square root of both sides. So we want to get x squared by itself, and again, that's how we solve linear equations. Alright, so we're going to get this x squared by itself, so we're going to get rid of this positive 1 by subtracting 1 from both sides. We'd have 2x squared is equal to 17 minus 1 is 16. Then to get rid of this 2, we would divide both sides by 2. And of course the 2's cancel, leaving me with the x squared by itself. That was the goal here when we started. And then 16 divided by 2 is 8. Once the squared term is by itself, use the square root as an operation to both sides, and square and square root will cancel, and it gives you x. X is by itself, so that's what we wanted. Every time you use the square root as an operation in solving equations on the number sign, you have to preface it with plus or minus. There it is. And the way we'll deal with the square root of 8, we'll simplify it in this step. And the square root of 8 is the square root of 4 times the square root of 2. Okay? And now we know what the square root of 4 is. That's 2. And then there's our final answer. X is equal to plus or minus 2 square root of 2. We need to see this as two answers. One with plus, one with minus. Okay? You try one. Okay, I have a quadratic equation without an x to the first term. I'm going to isolate x squared. I'll do it by getting it by itself. Start by adding 6 to both sides. So we add 6. We get 4x squared equals 48. Okay, getting x by itself, we divide by 4. We get x squared. 48 divided by 4 is 12. We take the square root of both sides. And square root cancel. First thing I write on this side is plus or minus. If you leave the plus or minus off, class, there's two answers. And if you leave the plus or minus off, you're giving me the positive one and you're leaving the negative one out. And that's only half the answer, so it's at least half off. And then take the square root of 12, and we'll break that down into the square root of 4 times the square root of 3. And the square root of 4 is 2 square root of 3. There's our answer. Plus or minus 2 square root of 3. Okay, try this one. Okay, same thing here. We don't have the x to the first term, so we'll isolate x squared. We'll start by subtracting 3 from both sides. And don't forget this sign now, so it comes down with the 5. We get negative 5x squared is equal to a negative 12. We divide by negative 5 to get x squared by itself. We get x squared is equal to negative over negative is positive, and we've got a fraction here. Okay, we know how to work with fractions. We take the square root of both sides, put a big square root sign on that. X is equal to, don't forget the plus or minus. And 12 over 5 doesn't simplify, so we'll go ahead and break that down into the square root of 12 over the square root of 5. Square root of 12 will simplify, so I'm going to go ahead and simplify it now. I know I have a radical in the denominator I've got to deal with, but I've got to simplify 12. I'd rather simplify before I multiply it by something, so I'm dealing with smaller numbers that I can recognize what goes into them. And that's going to be, well, let's see, the square root of 12 is equal to the square root of 4 times the square root of 3. And the square root of 4 is 2, so the numerator becomes 2 square root of 3, simplifying the square root of 12. Over the square root of 5, and then I'll rationalize the denominator by multiplying by the square root of 5 over the square root of 5, and in the numerator plus or minus 2 square root of 3 times the square root of 5, multiply those radicands, the square root of 15. In the denominator, square root of 5 times the square root of 5 is 5, and there's our answer. Alright, that one wasn't quite as easy as that last one. Had that fraction in there. Okay, another example here is this time we don't see the x squared, but it's in a parentheses that's being squared, and so we basically solve this one the same way as we do the last one. let's see, I think there's a tendency with these to think that you're supposed to distribute that exponent. You don't distribute over addition. You could over multiplication, but you don't just simply say x squared plus 5 squared. It's not what you get. The approach we're going to take here is we're going to treat this parentheses as if it was the x and get what's being squared by itself. Okay, so I'm going to get rid of this 1/3 by multiplying by 3 over 1, and we think about that. 1 over 3 times 3 over 1, that's going to cancel, isn't it? So the 3's cancel and the 1's cancel, and I'll multiply by 3 over 1, and I'll just write it as 3 on this side. So what I get here is x plus 5 to the second power equals 21. So I've got whatever's being squared by itself. I want to get rid of the square so I can get into the x plus 5, and to do that I simply take the square root of both sides. So taking the square root of both sides, square root and square cancel. I get x plus 5 equals, don't forget the plus or minus the square root of 21. Now, yeah, you can take 21 and break it down into 7 times 3, but neither 7 nor 3 are perfect square factors. So there's no need to write that out as 7 times 3 because it doesn't go anywhere. It doesn't simplify. We leave that as the square root of 21. And the next thing is to get x by itself. The only thing we got to do is get rid of that plus 5, and we subtract 5. In my class, I want you putting that minus 5 in front of this plus or minus, okay, not behind it. So on this side, we get x, and x is by itself, and then we have negative 5 with a plus or minus the square root of 21 at the back. Okay? Now, what I want you to be aware of is that this is actually two different answers. We can stop right here because we really can't add and subtract the square root of 21, a radical. We can't add and subtract it to an integer. So we stop right here, but we need to understand that this answer is really x is equal to negative 5 plus the square root of 21, and it also represents x is equal to negative 5 minus the square root of 21. Okay? But you can stop with this, but you need to understand it means this. What if the answer had turned out? It's all right, what if? It doesn't. It's got nothing to do with this problem, except you're going to run into this in the future. So what if the answer turned out to be x is equal to negative 5 plus or minus the square root of 16? You wouldn't stop there because you know the square root of 16. So you'd have to, on the next step, write x is equal to negative 5 plus or minus 4. You wouldn't stop there because you can actually add and subtract 4, an integer to another integer, whereas in this problem it was the square root sign that made us stop and wrote this as the answer right here. But here we keep going and we have to write it out as 2. So it's negative 5 plus 4, and it's x is equal to negative 5 minus 4. So here the correct answers would be negative 1 and x is equal to negative 9. Again, it's a what if. It has nothing to do with this problem here, but you're going to see some times where that turns out to be a perfect square factor. You'd have to, like 16, and you'd have to evaluate it, and then you'd have to give me two answers here. Okay? Let's go ahead and try another one. Alright, so in this one, I didn't leave much room up here, but we're going to multiply by 2 over 1, and that's a fraction, 1 over 2. And on this side, I'll just write it as 2. And then the fractions cancel, and we get x plus 8 squared equals 28. Get rid of the squared by taking the square root of both sides. When you do that, you have to put plus or minus on the opposite side, the side that's got just the number. And the square root of 28 is the square root of 4 times the square root of 7. We're going to simplify this. And that's 2 square root of 7, so I'll write 2 square root of 7 here. And we subtract the 8 from both sides. We remember to put it up front. X is equal to negative 8 plus or minus 2 square root of 7. And that's our answer. Don't be tempted to add 2 and 8 here because 2 is connected to the square root of 7 by multiplication. You'd have to multiply before you could add or subtract, and since it's got a square root on it, that's going to keep us from doing that. And that is the answer. And that ends this video. Thank you for watching.